What specific problem does AXBENCH address in the context of language model control methods, and why is this problem significant in current research?
AXBENCH addresses the problem of evaluating language model (LM) control methods, particularly representation steering, in a realistic and scalable manner. Existing benchmarks have primarily assessed only a few methods at toy scales, lacking comprehensive evaluation across open vocabulary concepts and long-form generation. This is significant because it limits our understanding of how effective representation steering can be compared to established techniques like prompting and fine-tuning. By introducing AXBENCH, which generates synthetic training and evaluation data from natural language descriptions, the work aims to provide a more robust framework for assessing the utility of various model control methods. This advancement is crucial for pushing the boundaries of LM interpretability and steering, ultimately enhancing the alignment of LMs with human goals and values.
How does the AXBENCH methodology work? Please illustrate the step-by-step process involved in training and evaluation, specifically regarding the generation of training and evaluation data from natural language descriptions.
The AXBENCH methodology involves a systematic process for generating training and evaluation data from natural language descriptions of concepts. First, it begins with genre labeling, where the model selects a genre, text, code, or math for each concept. Next, seed instructions are randomly sampled from an instruction pool corresponding to the chosen genre. For positive examples, the model generates responses that incorporate the concept based on these seed instructions. Negative examples are created by sampling seed instructions from all genres and generating responses without additional instructions, ensuring they do not activate the concept. Finally, hard negative examples are generated by identifying semantically related but contrasting concepts, which are then used to create a set of responses that should not activate the target concept, thus forming a comprehensive dataset for training and evaluation.
Can you provide a concrete example demonstrating how the REFT-R1 method operates in practice, including the types of inputs and expected outputs?
The REFT-R1 method operates by utilizing a weakly supervised approach to learn steering vectors from labeled datasets. In practice, it takes as input a list of natural language descriptions of concepts, which are then used to generate training and evaluation data through an LLM. For example, if the input concept is climate change, the method would generate positive examples that explicitly incorporate this concept in responses, alongside negative examples that do not. The expected output would be a set of steered responses that effectively reflect the presence of climate change, rated by an LLM judge based on their relevance and adherence to the concept. In the AXBENCH evaluation, REFT-R1 demonstrated competitive performance against traditional methods like full fine-tuning and prompting, indicating its effectiveness in steering model outputs towards desired concepts.
What advantages does AXBENCH offer over previous benchmarks for evaluating model steering and concept detection methods? Please identify any specific improvements in terms of methodology or evaluation criteria.
AXBENCH offers significant advantages over previous benchmarks by evaluating model steering and concept detection methods in a more realistic and scalable setting. Unlike earlier benchmarks that often relied on limited tasks or fixed prefixes, AXBENCH utilizes a comprehensive approach by generating synthetic training and evaluation data from a list of natural language descriptions of concepts, allowing for open vocabulary evaluation. It assesses methods along two utility axes, concept detection and model steering, using labeled synthetic data as ground truth and an LLM judge for long-form generation evaluation. Additionally, AXBENCH introduces a novel weakly supervised method, REFT-R1, which demonstrates competitive performance against traditional fine-tuning and prompting methods, highlighting the potential of representation steering. Overall, AXBENCH's extensibility and the ability to incorporate new evaluation tasks as techniques evolve represent a significant methodological improvement in the field.
What metrics or benchmarks were used to validate the performance of AXBENCH, and how do these metrics ensure the reliability of the results obtained?
AXBENCH validates performance using two primary metrics: concept detection and model steering. For concept detection, it measures classification performance on a held-out set of labeled synthetic data, ensuring that the methods can accurately identify the presence of concepts. In terms of model steering, AXBENCH employs an LLM judge to rate the quality of steered outputs across three relevant axes, which provides a nuanced evaluation of how well the model can be directed to produce desired behaviors. The benchmark includes a dataset called Concept 500, which consists of 500 concepts, allowing for a comprehensive assessment of various steering methods, including the novel REFT-R1. By comparing these methods against established baselines like prompting and fine-tuning, AXBENCH ensures that the results are reliable and reflect the effectiveness of representation steering in a realistic setting.
What are the limitations of the AXBENCH methodology regarding its extensibility to different tasks, or its reliance on specific language model architectures?
The AXBENCH methodology has limitations in its extensibility and reliance on specific language model architectures. While it is designed to be extensible to arbitrary concept descriptions, the current implementation is primarily focused on tasks generated from, say, concept lists for specific models, namely GEMMA 2-2b and GEMMA 2-9b, which may restrict its applicability to other architectures or tasks. Additionally, the benchmark evaluates a limited set of steering methods, with only the novel REFT-R1 showing competitive performance against prompting and fine-tuning, indicating that the effectiveness of steering methods may vary significantly across different model architectures. Furthermore, the reliance on synthetic data generation from a specific LLM, GPT-4o Mini the 18th of July 2024, for training and evaluation could introduce biases or limitations in generalizability to other models or real-world applications. Lastly, the benchmark's focus on specific layers of the models may not capture the full range of behaviors across all layers, potentially limiting the comprehensiveness of the evaluation.